Great. Thank you so much for that very energetic introduction. That definitely woke me up. So thanks, everybody, for coming back after the break. As Angela said, I'm sure that you've learned a lot over the past day and a half, and I hope you have a little bit more space for 2 last talks. So what I'm going to talk about today, or the title of the talk, is Reaching for the Sky with JavaScript. And what I mean by that is that we're going to learn how to get live data from flying airplanes with an antenna. So I'm not talking about pinging an API and getting your flight status. I'm talking about using a device like this. That's actually an antenna, and like going outside. We're not going to go outside today, but I'll show you, videos. And you're pointing it at an airplane, and you actually get live data that airplanes are broadcasting all the time when they're flying. And we're going to do all of this in JavaScript. So before, I already got introduced, so I can kind of skip that. So yes, senior dev advocate at Stripe to pay the bills, and then author and creative technologist. That's kind of like more of like a self-proclaimed title. I love to experiment with technology. Most of the time, I do use JavaScript because, if I use JavaScript on my job, then I don't have to learn all of the different programming languages. But I love to push the boundaries and see what are all the weird stuff that we can do with the knowledge that we learn on the job, but just do more creative, outside of the box thing. And when I'm not in front of a computer, I like to be in 3D in the world, in nature, and solo travel as much as I can. So before, an important thing I need to say before I start explaining, how to do this thing, is that what I'm going to show you is legal. And the reason why I'm saying that is because, when you talk about tracking airplanes, some people get a bit weird. And when I shared my side projects on Twitter the first time, somebody replied tagging the FBI, and that was not something I was super happy about. So it is legal. If I was doing illegal hacking planes, I would not put it on Twitter. So there are things illegal that you can do. I'll mention it at the end. I will tell you not to do it. But if you want to learn about this, there's other people who are doing the illegal stuff for you, and you can just learn. But what I'm going to show you, all the code and stuff, that part is legal. And another point that I wanted to make is that all of this started back in 2017. This project is inspired from a talk by Thomas Watson that he gave at .js in Paris that was called Getting Data from the Sky. And his project was, he built a Node.js module that was kind of doing exactly the same thing. I'm totally inspired by him. So he had the same, similar, not the same antenna, but a similar one. And using Node.js, he was getting live data from airplanes, and then I think using WebSockets, he was streaming the data to the front end and having little emoji planes on Google Maps. And when I watched this talk, I was like, whoa, I didn't know you could do this in JavaScript. And I learned by doing, so I started looking into recreating this project. But every time when I work on my side projects, I try to add a little twist, a little personal touch, push it a little bit further. And so instead of using a Node.js module, I thought, can you remove the server-side totally and just do it in front-end JavaScript with web APIs? Is it possible? And yeah, otherwise I wouldn't be here. So this is what we're gonna do today. So we're remove server-side all on the JamStack architecture. So all in front-end JavaScript. So what do you need if you want to do something like this? So first, you need a piece of hardware. And the one that I have here is, so you need a software-defined radio, that's called an SDR as well, and a little antenna. There's a lot of different software-defined radios and antennas that you can buy as well. That's just the one that I have. As long as you can receive data at the frequency that you're interested in, which for us is going to be 1090 megahertz, then you'll be fine. So that's for the hardware side. That's plugged via USB to your computer. And then on the software side, we're going to use the WebUSB API. And that's going to allow us to connect to our USB device and start to get raw data. But then from raw data, you need to kind of extract something that is useful. So we're going to use vanilla, pure JavaScript. So no framework needed. You can do it in React if you want. You could do it in Angular. I don't care. As long as you can write vanilla JavaScript, you'll be fine. So there's no framework war here. And you can do everything from scratch if you want. Otherwise, you can use libraries that other people have created. One of them is RTL-SDR.js by Sandeep Mistry, and the other one is Mod-S Demodulator by Thomas Watson. So you kind of have some options. If you just want to get started, you can use libraries that are already built, and then you can kind of reverse engineer and try to do everything yourself. But before talking about code, I thought I would try to explain a little bit how antennas transmit information. So let's talk about radio waves. This is like, obviously, I have a very limited time for this talk, so it's not going to be a deep dive. This is going to be very, very high level, talking about electromagnetic waves. So I have an antenna here, so I'm just going to, I'll play that later, but first I'm going to try to show you here. So I have my antenna here with like a dipole antenna, so 2 poles. You have a positive side and a negative side. And at first, right now, nothing's happening. There's no power, it's not plugged in. So when you plug in your antenna or your software-defined radio, it starts to create an electromagnetic wave around the 2 poles. And when data is then starting to be transmitted or received, you have the electrons in the antenna that start to oscillate between the positive pole and the negative pole. So it's like disturbing the electromagnetic wave that was there, and then the electrons oscillate at different amplitudes and whatever. And as it does it over time, you kind of start to have that shape of wave. So just to recap, here you have the antenna, and then when you apply some kind of electric current, you start to have the electrons oscillating, and then from the 2 sides of the antenna, and it disturbs the electromagnetic wave and does radio waves over time. So like a 1-minute explanation of electromagnetic waves. So if you're interested in this, obviously there's people who explain this a lot better than me online. But just to get started to try and understand how this works, I thought it was pretty cool. So okay, we have waves that are transmitted through the air at the speed of light. But how is actually information encoded in these waves? So one way to do this is usually like an alteration of current. It could be a pulse on and off, or just a pulse like a little bit more current, a little bit less. So you start to encode data. You can think of data as our ones and zeros. So even when you write your code, it ends up being converted to binary. And with alteration of current, you can encode a 1 as like a little bit more current and 0 as a little bit less. And it starts to be sending it in waves. So yeah, all information ends up being encoded in 0s and 1. And this is like our transmitter antenna. So electric current flowing through the antenna, it starts to do the wavy wave in space. And it does it at a certain frequency. So you can pick the frequency at which you want to transmit. But for us here, it's 1090 megahertz. And on the other side, though, you have to have the receiver antenna. So I have like my transmitter antenna, like pew, 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 and then I have the receiver antenna on the other side that is also plugged in, that also has an electromagnetic wave here. And as it receives the data that comes in waves, it also makes the electrons fluctuate into the different sides of the dipole antenna when it receives, and then all of that signal can be re-encoded back into the original signal. So if your antenna is tuned to the same frequency as the transmitter, then it gets that data and you can re-encode it into 0s and 1s. Okay, so cool, antenna, waves, cool. So what does it have to do with planes? So now let's talk about planes. So planes have a lot of different sensors, and they constantly need to broadcast information. So first of all, to ground control, so that airports and stuff can know which planes are passing by and exchange information between them. But there's not only one plane in the sky at a time. There's tons of them. So other planes also have to communicate to ground control, but most of all, they have to also communicate with each other. And the way that they do that is with their onboard antennas. So there's a lot of different information that planes need to broadcast. And the one that you can pick up with an RTL SDR or another kind of SDR and antenna is information that is public, that is unencrypted. That's why it's legal. If they really wanted to, they could protect and make it encrypted, but they don't. And you can do this with using mode S signals and the ADSB system. So that's going to be the communication protocol that is going to shape the data in a certain way. So when we talk about mode S signals, this is kind of like the shape. So you have a preamble, and then you have the data that has between 56 and 112 bits. So why am I showing you this? Well, when you get raw data from an antenna, you need to be able to decode it. And to decode it, you kind of need to understand the communication protocol that is used. So what is that data made of? So then when you have an ADSB message, because a mode S message is not necessarily an ADSB message, it can be other types as well, but for planes specifically, we want ADSB messages. So that is kind of like the structure of any ADSB message. So that's the 112 bits that are the second part of the mode S signal that I showed before. So here, hopefully it's not so small, but like the most important part is the thing on the right. So here's the table of how you would, let's say the structure of then an ADSB message. So we have 112 bits, and the first 5 bits, for example, contain information about the downlink format. But we're more interested in the bits between 33 and 88, so kind of like the one below the middle line, that is going to contain information about the message that is broadcasted by plane. So when I say message, I don't mean like what the pilots talk to each other like on the radio or whatever. I mean message like the position, the speed, the altitude and angle and all that stuff. So at this point, I talked about antennas and I talked about broadcasting information, but how do we actually get that in the browser? Because if you're a JavaScript dev, that's what you want to know. So let's move on to the WebUSB API. So if you've never used this API before, it's a browser API. I've mostly tested on Chrome. I don't know if it's implemented in all browsers, but for me, at least on Chrome, it works. And it allows you to connect to devices that are plugged into your computer via USB. So when if you don't tinker with an antenna, but you have like a keyboard or a camera plugged in or whatever, you can start to get data about your USB devices using that API. So the first thing you need to do is to get your USB device to actually communicate with the browser. So to do this, you need to call a navigator.usb.requestDevice, and you can pass in some filters. So the filters would be the name of, or the ID of the device, to make sure that you're really isolating the one that you actually want to communicate with. So here I just created like a fake variable, but you would pass in the name of your device if you wanted to not see all of the USB devices connected to your computer, but only the antenna that you're interested in. And then when you've kind of like selected that device, you just call open to kind of connect to it. The next step would be to select the configuration. And most devices only have one, but it's possible that they have more. And what that configuration does, it returns information about how the USB device is configured. So the maximum power consumption, or how the device is powered, and things like that. And then from that configuration, you start to look at how many interfaces it has. So the RTL SDR device has only one interface. These things, you can figure it out in the data sheet of the hardware device that you're plugging in. But if you don't know it, you can kind of play around with different values. And if there is no configuration that exists or no interface, the WebUSB API will kind of scream at you anyway. So that's kind of useful to be like, oh, if I try to claim interface 1, it will tell me there's no interface with ID 1. So you kind of if you don't have access to the data sheet, you can kind of tinker around with IDs until you find the right one. And then if you were doing everything from scratch, so if you're not using pre-built libraries, you would call the method control transfer to indicate to the USB device which frequency you want to tune the antenna to. But as I'm using RTL SDR library, the syntax is a little bit different. The rest of the code is abstracted into set, I would call set sample rate to indicate the amount of data that I want to track. And then set the frequency. So the center frequency is going to be our 1090 megahertz, which is the one at which the ADSB signals are transmitted. And then you would read the samples that returns an array buffer. And to be able to read the values inside it, you transform that into an array of 8-bit integers. So at this point, there's maybe a tiny bit more code than this in my real application, but it's kind of, overall, it works like that. And when you're running this and you're plugging your device, you would get something like this. So it's like an array with a bunch of numbers in your browser. And at this point, it's like, OK, we kind of get data, but how do we turn that into a human readable information? So part 4, decoding the data. And at this point, this is where you demodulate the data. So here I'm using the mode S demodulator by Thomas Watson. And so I import it. And I call the process method with the data, as well as its length, and a callback method that will return. I keep on blowing air into my microphone. And it will return JSON data with the logic that has identified ADSB messages. So I don't have the time to go into too much details, like go line by line with the code on what mode S demodulator does. But I wanted to walk you through a bit manually how you would take raw data and then identify an SB message and then identify the rest of the stuff. So let's imagine that we start with this. So we have a bunch of raw data over bits of zeros and ones in the browser. And then we know that from the ADSB specs, we can see that, OK, the downlink format, so the type of the message, is indicated in the first 5 bits. And civil aviation And that's from like research. So civil aviation uses downlink format 17. So you know that the plane that you maybe took, to come here, it means it was broadcasting information, and if its downlink format had the decimal value 17, you know that you are dealing with a civil plane, like not military or anything. So the decimal value 17 in binary is 10001. And what do we have here? Oh, okay. So in our third message, the first 5 bits are 10001. Okay, so we know that in this particular message, and you can see my console log underneath, where it was just like, yeah, that's message ADS. We have here an ADSB frame. Cool, so we can start reading the rest of the message. So looking back at the documentation, we're interested in the message. Okay, what kind of information is in that bit of data? So the message is contained in bits 33 to 88. Okay. And then on the line just below, we see that to know which type of information, so the type code, because as I said, it could be the speed or it could be the altitude, we need to look at the first 5 bits, so bits 33 to 37. And then if we look at the documentation for type codes, we have what they could be, so the breakdown. If the type code is between 1 and 4, then the data that's going to be in that message is going to be around aircraft identification. If the type code is 28, then it's the aircraft status, etc. So what do we have here between bit 33 and 37? We have 10000 in binary, which is 16 in decimal. And what does that say? OK, so we know here that 16 is between 9 and 18. So we know that the message contains information about the position of the aircraft. So I'm going to stop here in terms of like going manually, but you would kind of go into this and you would decode the rest of the message based on the communication protocol and the specs that you can find online. So now that I talked about like waves and WebUSB and how you decode the message, I wanted to kind of show a little bit how it works in practice. So I would have loved to be able to demo that live, but I can't for a couple of reasons. First of all, we're indoors, and it's a hotel, so there's like levels above us that are going to just block any kind of waves. And second, I also checked the flight path, and there's no kind of plane flying just right above Cluj. So even if we were outside, even if I was like, everybody get outside, like that wouldn't work. There was just no planes, so it wouldn't have worked. But it means that if you're trying to reproduce that at home and you happen to live closer to the flight path, or you're training at the airport. I really wanted to try it at the airport, but then I thought it would be weird. So, but that would be awesome. It'd be like the best place. So what I'm going to do instead is where I live in Seattle, I do live under the flight path. Usually you'd kind of be annoyed at that because it's very loud, but that was perfect for this application. So I'm going to show a couple of videos. So here, first, you can see there's a plane. And if I do this, yeah, okay. So there's planes, and I'm on my rooftop, and there's like data in my browser. I'm just like, woo! So you can see. So some of the values you will probably notice are null. It's not because the plane is sending null. It's just that there might be some issue in my code, or like there's just like too much going on, and the SDR is often overheating. So, but sometimes like you can get data about the speed, and you have like a heading over there. But otherwise, there's like I have a second demo where I was kind of like more waiting for a plane. So like I'm on a rooftop, I'm waiting to get some data, and then I start to get some data. And what do I see in the distance? A plane. So as it's like while the plane is a bit far away, of course I'm not going to get data. And when it's in the right range for my antenna to pick it up, then I'm starting to get data about that particular plane. So what I'm going to just let it play. So the really, really cool thing is that sometimes, but not always, I actually get the specific flight code, and then I can compare it on a website like Flight Tracker or whatever, and I can be like, yeah, it is exactly the one that's passing over me in Seattle, so I could just double check that it was working. But yeah, so that's pretty cool. It's that you can be outside, point it at planes, and wait and get data, and all of this in vanilla JavaScript in the front end. So at the beginning of this talk, all of this that I just showed you is legal. I'm only listening. It's as if you were just listening to the radio or to a conversation. That's not illegal. But I want to talk about what is illegal now. So transmitting is illegal. And what I mean by that is that, so this SDR here, the one that I have, is only a receiver. So it only can listen to things, it cannot transmit. So if you want to track airplanes and you want to stay in the safe zone, you can use only a receiver and you'll be fine, you won't do anything illegal. But when we're talking about transmitting, the reason why it's illegal is that you can imagine that if you were trying to broadcast the existence of a plane that actually doesn't exist, it would cause some kind of issues for pilots. Like even if it was on a clear day, and like you can imagine I'm a pilot and I look around and my systems tell me that there's a plane like right beside me and I look and there's nothing. Like it's just some distraction that pilots don't need to have. But also you can think if I'm flying on a cloudy day, and actually you don't fucking see what's around, and there's my system is like, you know, like collision, whatever, like that's not cool. So obviously it is very illegal. Do not do this. I obviously do not do this, but some people do. So like there's researchers, there's like papers, I'm gonna assume that they know what they're doing, but I really like this paper called Ghosting the Air Traffic, and it's about ADSB spoofing attacks, which is exactly what I just talked about. So it's about creating ghost planes and trying to kind of do bad things with that and just confuse pilots or even ground control and just mess around with airplanes. So when I said that transmitting is illegal, in that case, yes, transmitting to planes is obviously not cool, but transmitting in general doesn't have to be illegal. And you can switch to another device that's like a HackRF1, which is one that I have here. And this one is a receiver and a transmitter, so you can do both things with that. So I thought that if you're not interested in planes, I would show you a couple of other projects that you can also do if you are looking into learning about SDR and waves and all that stuff. So quickly, a few projects before I finish. So if you have a Tesla, you can open the Tesla charging ports remotely using one of these antennas. So I mean, if you do it to yourself, it's fine. If you try to open another person's Tesla, that's also illegal. So, but I mean, you can try. But I saw actually when I arrived here, there was a Tesla in the parking lot. So I don't know if it's somebody here, but you could play with that. So the device that this person has is called a Porter Pack, which I think is like another type of transmitter as well. But the way that works is when you're opening, even just your car, like any car, you have your little like clicky thing that transmits data to the car, and you could record that data. If you know at what frequency it's transmitting it, you can record it, and then you could do what's called like a replay attack. So you record the signal, and then you transmit it to the frequency that you know your car is going to be listening to, and you can open it remotely. So most of the time, most cars implement what is called rolling codes, so the code shouldn't be the same, but there are still manufacturers that actually implement a clicker that doesn't have a rolling code. So if you capture the message once and you replay, and it will be the same all the time, which is like super not secure. But even if you don't have a Tesla, but you have an electronic garage door, that works as well. You could record your little garage thing and then replay it and remotely just play around with that kind of like waves. And again, if you try to open your neighbor's garage door, that's obviously also not legal. But if you're hacking yourself, like I do, it's fine. And another thing that is like I really want to do is receiving images from the International Space Station. So, I mean, obviously, that's something I haven't had the time to do yet, but I wanted to. I think the sound is going to be annoying for that one. I hope I can just like, okay. So it's like a sped up video, but you can see that here, this person lives in Tasmania, and the ISS is actually flying over the country. So you can see, I think the ISS might be flying over your position maybe like twice a day. And sometimes they send what is called SSTV images. So it's like slow scan TV images. And using an antenna outside, probably much bigger than the one that I have here. And if you're tuned it to the right frequency, which is 145.8, you can start receiving data really like from space. So this person here did not do it in JavaScript. You can see that he's running some kind of other softwares. But knowing that you can plug software-defined radio to the browser, and then you can get data. As long as you can tune it to the right frequency, you wait for the ISS to pass over you, and you try to decode that data and display images. I think it should be possible to recreate that in JavaScript, which is something that I would love to do next. But I'm not there yet. But even like if you're not interested in this, there's also you can create your own little radio and listen to either radio or listen to amateur radio people like who just talk to each other. And yeah, there's a lot more cool stuff that I wish I could show you, but I will not have the time. So before I finish, I wanted to just share, if you want to take a picture, a slide of resources, of like tools that I've used, or if you're interested in learning more about the whole decoding of mode S signals, I really recommend the mode-s.org website. It's where I learned most of my stuff. I also wrote a blog post about the project that I just talked about, and there's a repo if you want to have a look. Yeah, overall, there's another application that I wish I could talk to you about, but also I feel like as I want to rebuild it, once I say it out loud, then I'm going to put pressure on myself to actually build it. So I'm just going to keep it a secret for now, and maybe I will come back once I would have built it. But anyway, so what I love about this is that you can use the skills that you apply on your job to build forums or whatever website, and with the same JavaScript knowledge, you can just apply it to something totally random. And yeah, and you can start learning about electromagnetic waves and just antennas and all of that stuff, and hacking to Teslas. So it's, I mean, like, that's why I love talking about that kind of stuff. It's like you don't have to, it's like not out of your league at all, and that's what excites me the most. But anyway, on this, I am just on time. All right, thank you very much.